We're looking at proving that electrical field is a conservative field. It's conservative in nature. That is, the work that we do over here is independent of the path. All it matters is that we're looking at the final and the initial position. Now, to prove this, we have a charge Q, a point charge, and a test charge Q naught, which we are moving from point A to point B. Along this path or this path, it won't matter. Okay, so that's what we're trying to prove. Now, let RA be the position vector of point A and R be the position vector of point B. Now, let's consider point P, which on extending is this line. So this is your point P, which on extending, I think I didn't tell it right, which on extending is this line. So that's your position vector. At point P, the particle moves a length of dr. This extended line and this tangent makes an angle of theta. Now, any vector, whenever we get a chance of, looking at the angle and all of that, what do? Yes, we resolve it. So I can resolve this into two components. This is what? This is your perpendicular component, perpendicular to what? To R. And so this will be your parallel component. Agree? Take a second, have a look. The diagram should be clear. Okay, I hope that is clear. So the work done by external force in moving a charge very slowly from point A to point B, right? Since we are moving it very slowly, you'll end up with this formula. This we have seen from the start. Now, when I open up the dot product, I end up with cos of theta. This is hypotenuse and we have theta. Hypotenuse into cos theta will give us what? Yes, it will give us adjacent side. Good. So this should be a second nature to you guys now. Now, also, if I'm going to substitute this, right? So we are substituting this actually. If you're substituting this, what will happen to the limit? Right? Limit A will become, will get converted to actually, is to be replaced with limit what? Limit RA. And limit B to be replaced with RB. So these are the things that we need to substitute. Again, in your in your integration, whenever you're substituting anything, the limits also has to change. So Fe remains constant. This is dr cos theta, which is parallel, the parallel component. Agree, guys? So let's open up. So we have the, force is not constant. It will vary. Rp. So this is K, Q, just a second. K, Q, 1, Q, not Q1 in this case. Q not Q, still not right. Okay. R square dr R. So when you integrate this, what will happen? Minus K Q Q naught integration of this component will give us minus 1 by R, RA to RB. Right, guys? Because K Q naught Q is constant, we just have to integrate dr by R square, and integration of dr by R square is minus 1 by R. Again, this is not a complicated integration. If you're not able to understand this, means you need to go back to integration or learn integration. So this is 1 by RB minus 1 by RA. Again, all of this will come under integration. So you guys have to be thorough with that. So what is it telling? The work that we do depends on the constant Q and Q naught, that is the source charge and the test charge, and the final and the initial position. That's all. Is it not? So we can conclude that the equation shows that the potential difference between point A and B in a field, in this case electrical field, created by a point charge depends only on the radial component. So these are your radial component. Radial means related to radius, is it not? Radial coordinates actually. That's what they've written over there. Right guys. So your radial components, or in this case radial coordinates, RA and RB. This shows that electrical force is conservative. Very simple derivation. So here I'll explain the diagram again. You have a test charge and a source charge. So this is your source and this is your test. These are your position vectors. This is the path that the particle is taking. Along the path, I'm taking a small point, and in that point, this is your displacement dr. It makes an angle of theta with the radial component, and we are resolving it, right? So then we start off with writing the formula, which we know. So we need to substitute t r cos theta has to be substituted with your parallel component, because that's what the trigonometry tells. So once we have the parallel component, right? So limit a and limit b, the values at a and b has to be replaced with RA and RB. And we have your force, electrical force given by K Q naught Q by R square. So here everything else is constant other than the R value. So when you integrate that, we'll get minus 1 by R and so on and so forth.